Welcome to renenergy.com, your renewable energy and sustainability platform. At renenergy.com, we believe in the power of clean, sustainable energy to transform the way we live and work. That's why we offer a range of solutions for businesses and homeowners looking to switch to renewable energy sources such as solar, wind, and water. As the world seeks to transition from fossil fuels to renewable energy sources, solar-powered satellites have emerged as a promising solution for harnessing the vast potential of solar energy. These satellites have the advantage of capturing solar radiation in space without the interference of clouds, atmosphere, and nighttime, enabling them to generate more power than their terrestrial counterparts. However, despite their potential, solar-powered satellites face several limitations that could hinder their widespread adoption for global energy generation. In this video, we will explore these limitations in detail. Limitation 1. Low power output of individual satellites. One of the primary limitations of solar-powered satellites is their relatively low power output. Each satellite is capable of generating only 1 to 10 megawatts of power, which means that a substantial number of satellites would be required to make a significant impact on global energy generation. This can result in increased costs and complexity, as well as posing challenges for satellite deployment and management. Moreover, coordinating the power output from multiple satellites and integrating them into existing power grids presents a logistical challenge. The energy generated by these satellites must be efficiently distributed and managed to ensure a consistent and reliable power supply for consumers. This may necessitate the development of advanced power management systems and grid infrastructure, which can further add to the overall cost and complexity of implementing satellite-based solar power on a large scale. Limitation 2. Transmission challenges through heavy clouds and rain. While solar-powered satellites can transmit power through most atmospheric conditions, they struggle to beam energy through heavy clouds and rain. This limitation can reduce the efficiency and reliability of satellite-based solar power, particularly in regions with high levels of cloud cover or precipitation. To overcome this challenge, researchers are exploring ways to optimize the transmission of energy through the atmosphere, such as by developing advanced beam-forming techniques and adaptive optics systems. These innovations may help to minimize the impact of atmospheric conditions on energy transmission, but further research and development are needed to fully address this limitation. Limitation 3. Safety concerns and weaponization. The use of laser beams to transmit energy from satellites to Earth raises safety concerns, such as the risk of blinding or inadvertently causing harm to humans, wildlife, or infrastructure. To mitigate these risks, it is crucial to design and implement safety measures, such as fail-safe systems and beam control mechanisms, that can prevent accidents and ensure the safe operation of satellite-based solar power systems. Furthermore, there is a potential risk that this technology could be weaponized, which could lead to international security issues and disputes. Addressing these concerns requires the establishment of international regulations and agreements that govern the use of satellite-based solar power, as well as the development of monitoring and enforcement mechanisms to ensure compliance with these regulations. Limitation 4. High production and deployment costs. The production and deployment of solar-powered satellites require substantial financial investment, with costs potentially reaching tens of billions of dollars. This includes the expense of launching numerous satellites into space and the need for space-based assembly. These high costs may deter governments and investors from supporting the development and deployment of this technology on a large scale. However, advances in space launch technology and the growing commercialization of space could help to reduce the costs associated with satellite production and deployment. For example, the development of reusable rockets and the increasing availability of low-cost launch services may make it more affordable to send satellites into space, thereby making satellite-based solar power more economically viable. Limitation 5. Large terrestrial receiver infrastructure. To capture the energy beamed from solar-powered satellites, large terrestrial receivers several kilometers in diameter are required. The construction and maintenance of these receivers can be expensive and challenging, particularly in densely populated or environmentally sensitive areas. Additionally, the land required for these receivers could compete with other land uses, such as agriculture, conservation, or urban development, potentially leading to conflicts over land allocation and use. To address this issue, researchers and engineers are working on the development of more compact and efficient receiver designs, as well as exploring the possibility of integrating receivers into existing infrastructure, such as rooftops or highway medians. These advancements could help to minimize the land requirements and environmental impact of terrestrial receivers, making it easier to integrate satellite-based solar power into existing land use patterns. Limitation 6. Satellite repair and maintenance difficulties. The long distance between Earth and solar-powered satellites makes repair and maintenance nearly impossible. Consequently, any malfunctions or damage to the satellites could result in a significant loss of investment, as well as a reduction in the overall efficiency and lifespan of the satellite system. This limitation highlights the importance of developing robust, reliable, and durable satellite designs that can withstand the harsh conditions of space and minimize the need for maintenance and repairs. In response to this challenge, researchers are exploring the use of advanced materials and technologies to improve the resilience of solar-powered satellites, as well as investigating the potential for autonomous, self-healing systems that can detect and repair damage without human intervention. Additionally, advances in robotic and autonomous systems could enable the development of space-based repair and maintenance capabilities, allowing for the servicing of satellites in orbit. Conclusion. While solar-powered satellites offer a promising solution for harnessing solar energy on a global scale, there are several limitations that must be addressed before they can become a viable option for meeting the world's energy demands. Continued research and development in this field are necessary to overcome these challenges and unlock the full potential of satellite-based solar power. As the global community works together to tackle the pressing issue of climate change, it is essential that we explore and invest in a diverse array of renewable energy technologies, including satellite-based solar power. By addressing the limitations outlined in this video and leveraging the opportunities presented by advances in space technology, satellite-based solar power has the potential to play a crucial role in the transition to a sustainable and low-carbon future. Thank you for choosing ReneEnergy.com as your go-to source for all things renewable energy and sustainability. With our YouTube channel, we explore the latest developments and innovations in the field, including hydrogen fuel cells and the use of AI and machine learning to optimize energy consumption. If you're ready to take the next step towards a cleaner, more sustainable future, visit us at ReneEnergy.com and discover the many ways we can help you transition to renewable energy. Thank you for watching and subscribing. Stay up to date on all the latest news and insights by subscribing today.